So it really came as somewhat of a surprise to me. I've been doing concurrent programming in C, a little bit in C++ for about 17 years now. And you forget that the standard prohibits multi-threaded address spaces. It's as simple as that. So first I'd like to talk about what this task is not. It's sort of breaking new ground for me. I'm not introducing a new synchronization mechanism. I'm not introducing a new use of or way to test the synchronization mechanism. And just, again, this is not a comprehensive overview of C 0x. This is something that is a very large standardization effort. There's a URL up there you can take a look at that's got all sorts of things from, believe it or not, garbage collectors to memory barriers, which I'll be mostly talking about, to all sorts of things that have nothing to do with concurrency, just new features of the language. Since I've been mostly working in memory ordering, I'll be talking mostly about that. I'll give a quick overview of some of the other aspects of the concurrency in the standard as well. So why should C programmers care? I mean, there may be C++ programmers in the audience, things like KDE and a number of other things are written in C++. I'm sorry? Ooh. I don't know if they have that amendment in this country, but I don't know. Oh, okay. Well, we're set then. All right. So the thing is, one of the things they did here that was actually quite good and a little bit unusual is both the C and the C++ guys got together ahead of time and said, look, we need concurrency and we'd like maximum compatibility that makes sense. So what they did was they said, okay, C++ guys go first because they have the more complicated language, it's going to have the most constraints. They didn't quite put it that way, but that's how I heard it. And therefore, the C guys participate in the standard. There are a number of they co-locate their meetings, in fact, and they'll have both people on the committee. And then the idea is when the C++ standard is complete, it's adapted to C. And in fact, a number of the working papers have C bindings in the document itself, even though it's a C++ standard, just so they make sure that they keep the compatibility possibility there. So why did somebody like me end up messing with standards, right? I mean, you saw that stuff on the previous slide. Standards are supposed to validate existing use, and that's certainly not what my work has been about. Well, I was working on a C++ project for DARPA, and this was an embedded communications application based on Mach. C++ had some things in it, or lacked some things that we needed, so I took C++ documents and marked the heck out of them. But the committee actually did take this fairly well. There was some disappointment on one of this because he wanted to get back to sleep, but we had more stuff to go through. But no, that was 1990. So yeah, I attended one meeting in 1990 and then didn't until recently. So fast forwarding to 2005, I hear some rumor that C and C++ are standardizing memory ordering and that maybe I should get involved. And that didn't surprise me because the Java guys did it a little before that. So I quickly searched Google and don't find anything. And I went back to tearing my hair out trying to get the first real-time RC implementation working.
At least that part was successful.
We hope so. Tearing hair out. Oh, yeah, yes. Not quite as successful as some, but yes, definitely progress in that. Anyway, the fast forwarding to late 2006, some people are really concerned about this. They're concerned that it's favoring Itanium, and that's not their favorite CPU. I'll leave you to guess which one their favorite CPU is. This time you Google it, and it was right there. I could find it. So I joined the mailing list, and usual thing, right? You join a new group, you kind of lurk for a few weeks and try to figure out what's going on. Well, that didn't work in this case. The concurrency subgroup had a really high opinion of Linux. I'll let you read those. And as a result, with that and some other things, I was able to stay lurking for about 3 days. And even after I stopped lurking, the high opinion of Linux persisted for some time. There were some exceptions to this. I'll get to that later. But anyway, I had a lot of talking to do in Oxford and elsewhere. So we talked about this a little bit. We've been doing concurrency in a lot of different projects, not just the kernel, not just the Linux kernel, even within kernels, for a long time. The trick is that we always use non-standard extensions, always. So in the Linux kernel, we have ASMs, and these have things for memory barriers. We use the funny little memory attribute to make sure that the compiler doesn't mess us up. And in fact, the compiler writers really don't think much about concurrency. It doesn't really enter their mind. You get things like, hey, wait a minute. If you're doing that, then the result's undefined. So right here in the standard. So I can do whatever I want, get out of my face. We're going, but we got to have this work. And the other thing is that, well, we've had more than a few GCC compiler bugs that have messed up the Linux kernel. I'm sure other projects have been affected as well. So there is some reason for their skepticism, right? I mean, they're not totally blowing smoke when they say this stuff is, I mean, if you look within the confines of the standard, the current standard, there's no way you can implement CRCU. It just won't work. The compiler can mess you up. So what are the real problems? We got 4 of them here. There's more. These are 4 representative ones. The C compiler is totally within its rights to refetch variables anytime it wants. I mean, those temporary variables you do, the auto variables, they're just there. I mean, if the C compiler wants to, it can just reevaluate the thing that moved it into the variable and do the assignment twice. We'll see a couple slides what this can mess you up. Some of you, I think, are very familiar with this. It can fetch variables piece at a time, even basic types. If it wants to do a store, if it has some really snazzy vector operation, it can just go blam and knock out a bunch of memory and then just fix up a few pieces. It's within its rights to do that. It's nothing stopping it from doing it. It's also pretty liberal in what code reordering it can do. Now you can fix these with non-standard extensions and also by beating up the compiler guys until they eventually give up. But that latter especially requires constant attention, right? You beat one up, and then some other guy comes up you haven't beat up, and he forgets, and it's intermittent. It just keeps going forever. Let's look at refetching variables. That code on the top there, pretty simple. We pick up a global pointer named head. We do something with one field of it. We do something in another field of it. What you'd expect, you pull it up, stuff it in a temporary named P, right? And then you use that temporary P. So even if you're changing head all the time, you should just get a pointer to one structure. The compiler, if you look at the standard, is totally within its rights to compile that code as if it was this. The only difference is that we refetch from head here. All right? And that can be a rather nasty surprise if there happens to be some other task that's modifying head concurrently with that. Why would they do it to us? Well, the x86 and 32-bit mode is one good reason. It doesn't have many registers. And you might be able to do that one without flushing registers. You do the ton on top, you might have to dump your registers and reload them. So pictorially, we have something like this. The green code is doing it right. The red code is doing it wrong. We've got 2 different structures. Head points to the one on top at the beginning, and then while we're doing this code, it switches to the one on the bottom. If you fetch the pointer only once, you're guaranteed to see either one or the other of those structures. But you'll get whatever one you get, you'll get A and B from the same structure. If the compiler, and the compiler is totally within its rights to do this with the current standard. If it decides to compile it like this, you might get A from the first structure and B from the second structure. And if you yeah, go ahead, back. Was that a question? Oh, okay. So, okay, well, I'm into concurrency. So the thing is that if you're looking at your code, it's really difficult when you're looking at that to keep in your mind that the compiler might have generated something down here. And if you got a huge amount of code like this, and Linux kernel does have quite a bit, right? You've got a lot of places you could look where the compiler might have messed you up. Okay, I'm done with my sentence. Question?
You may be coming to this, but if head was able to be changed, wouldn't you have declared it as volatile?
That is an interesting discussion. What would happen is that actually works in a very restricted situation. Okay, if and it would actually take care of this particular situation. Use a volatile cast, and it would force the compiler to pick it up, and if it needed to ditch it, it would have to dump it into a temporary. Okay. However, it would not handle some of the other things we'll be talking about later on. In essence, what it does is it makes it so you only get one, and that's one way to do it. The problem is, though, that what volatile means is kind of ill-defined, and you can't totally blame the C guys for that because volatile came along a long time before multiprocessing did, really. It was designed just for devices. But you are right. In this particular case, I believe you could get around that problem. The downside of that is that if you made that variable volatile, everywhere you accessed it, even if you had a lock and it couldn't change, it would fetch it every time you mention it. You'd be disabling a bunch of optimizations that you might want to allow. So on the one hand, vol doesn't take care of some of the other things I'll be talking about. On the other hand, if you declare the variable volatile, you may be prohibiting valuable optimizations elsewhere. Okay. Anyway, going on to the next one, piece at a time variable reference. So we have that same piece of code again. We pick up a pointer, we grab one field, we grab another field, dereferencing off of it in both cases. The compiler is totally within its rights to do this right here, strange though it may seem. It could have a little for loop and grab that pointer byte at a time. There's nothing in the standard preventing that. Of course, if some other task modifies head in the meantime, it could be painful. There are machines, however, where it is impossible to do the code that way, where you have no choice but to do this. Imagine an 8-bit machine with 16-bit pointers. C is required to work on those machines. Thank God the Linux kernel is not. So, again, the C, not only does the standard permit the C compiler to do this, there are machines in which there is no choice. Yeah, Grant.
But Linux is, in fact, doing that with 64-bit data structures and data. We have time as a great example of that, right? Where we have 32-bit architecture and 64-bit data.
That's true.
Issues around it.
It can, if you, depending on what you want to live with, and there are some architectures that do that. But the thing is that as far as I understand it, the Linux kernel requires that pointers. You're right, there are other data structures where you have the same problem happen, but with pointers, the machine is required to be able to pick up the whole pointer all at once.
Okay.
All right, but you're absolutely right. If you have a larger structure, life is hard.
DNA adder D.
That could be a problem. Or just larger structures. Okay, so you're right, I was a little bit, I gave a specific example, and this, fortunately, only applies to that specific example of pointers, so that's absolutely correct. And pictorially again, we got something like this. We have a head that points off somewhere, and it's hard to see, but the bottom two are a little bit different color than the top two. I got better contrast up here than you got down there. But I've got a head prime, as you can see the little prime there, which may also be invisible in the back. Yeah. Anyway, if I do it this way, I'm guaranteed, I don't know which pointer I'm going to get, but I'm guaranteed to get one of them and get the whole thing. If I'm doing it the other way on the side, well, I might get kind of a half and half pointer. And I might be addressing something I didn't want to address, or I might be addressing non-existent stuff that will cause the machine to crash. I might be accessing stuff in the kernel that damages the hardware. I mean, that's kind of a bad design practice, but it could happen. So this is not something we want to be having happen. Collaborating adjacent variables. Suppose we have a structure like that. I might get bored with the old example, so I picked a new one. So we've got a structure that has a pair of shorts in it. So it's an int, if in 32-bit mode it's an int and long. I guess in either mode it's an int and long. And let's say we have code that assigns 0 to it and assigns 42 to the second piece. So we zero out the A and we put a 42 in the B. The compiler is totally within its rights to generate the code like that. Zero the whole mess, put a 42 into B. And there are cases, in this case, it seems like it's why would you bother. You might bother if you had a machine where assigning with shorts was much more expensive than assigning with ints, which has happened sometimes. But if you have machines with vector units, this sort of optimization can be very compelling for the compiler guys. Grant?
An example of that, if the 16-bit value or 32-bit value is not aligned properly, sometimes compilers will break them down into smaller pieces for you.
That's right. And that's why alignment is so really important in kernel data structures.
Can you just repeat the questions when they ask?
Oh, I'm sorry. The point Grant was making was that if you have a pointer or an int or something that's broken across an alignment variable, so you have a 4-byte quantity that's not aligned to 4 bytes, the compiler might find it the machine might work a lot faster if you pick it up a piece at a time than if you pick up the whole thing. And the same thing happens with stores. This is kind of in the other order. So the thing is that some other task watching might see B being 0 momentarily, even though logically in the program flow, B equals 0 might never have occurred. All right? And again, we've talked a couple of cases where this could happen. And in pictures again, you coded it to happen like this. Let's say that A and B were initially 1 and 2. So you made A be 0, and then B would 2 at that point, and then you had B equals 42. If it did it the way the compiler wanted to do it, we end up with something over there. We end up with both A and B being 0. Logically, that never occurred, but some other task might see that value. And again, that could be a great disappointment to code that didn't expect that. So the bottom line here, again, is the compiler assumes there are no other threads. And that's baked in the compiler. It's baked into the standard at the current point. That's what we're trying to change. Reordering code. Suppose you do something like the top there. You fill out a data structure, and you publish a pointer to it. Well, if you don't tell it otherwise, the compiler is free to publish the pointer and then fill the data structure in. And why would it do this? Again, there may be register pressure. Maybe that has values in some registers and has special restrictions on the registers. x86 comes to mind again. It has to do a lot of other machines I've used. And the thing is, of course, that if some other task or even an IOQ handler happens to be watching, it might see something unexpected. Of course, it's not enough, and this goes back to the volatile question we heard earlier, it's not enough to prevent this compiler from reordering. If you have some other task, you also need to prevent the CPU from reordering. Preventing the compiler from reordering works if you're only worried about your mainline and an interrupter signal handler. But if you're worried about some other task, you need memory barriers as well. So again, going back and seeing what the diagram looks like, you coded something like this. You start off with not knowing what's in it. You just allocate it or something. You set A. You still don't know what B is. You set B. Now you know what they both are. And then you make this global F pointer point to the filled out data structure. Life is good. If the compiler does it the other way, well, you got the thing unknown what it is, and that's fine because nobody can see it. You point the pointer to it, that's bad because suddenly people are seeing an uninitialized data structure and trying to do something with it. And then you fill out A, but that's great for A, but B is still messed up. And finally, at this time, you're back to something reasonable. And these are kind of ugly, of course, because it isn't obvious from the code. And also, the probability of seeing it is very low. You've got a couple of memory accesses, maybe just 2 cache lines involved. Maybe only 1 if the pointer and the data structure happen to be in the same place. The chances of seeing that are very small. It's very difficult to test for. Again, the compiler assumes that there are no other threads. And it's specifically permitted to by the standard. We've gone through some of these, but it's good to sum them up. The C does this because of optimization reasons. Get better performance. A lot of existing compilers do this. There are strange CPUs for which there is no other way to get the job done. 8-bit CPUs. There have been CPUs that have large words but don't have any way of getting at subwords. You have to store the word and pick the word up and or it and then put it back to do a byte operation, for example. The Alpha, the old CC6600, a bunch of other ones in the past. The approach they've taken is to define an atomic type. And this is sort of like volatile, except that it actually has semantics across CPUs as well as just within a single CPU. Now, what they did is they preserved the old definition for non-atomic variables. If the non-atomic variable, if you have 2 people trying to write to the thing at the same time, or 1 person trying to write, another person trying to read at the same time, the results are still undefined. Okay? So for normal code, where there's no concurrency, the C compiler is within its rights to do all of the optimizations it ever did. What you do is you label the variables atomic so that it knows this variable is special and it has to generate the code carefully for it. And then, at that point, once it's atomic, an atomic variable can't participate in a data race. Data races apply to the other ones. You can use locks and things like that to make exclusive access to variables so that you have a normal variable you're doing inside a critical section. And the compiler is allowed to totally optimize that critical section just like it always did, which is okay if you're using locks and using them correctly. Nobody is looking while you're doing all that work. So that was sort of the compromise, to label things as opposed to prohibiting a whole bunch of optimizations. A logical next step would be to define memory barriers, but this was surprisingly controversial. On the other hand, given the things we've had through the Linux community about trying to define what the heck a memory barrier might mean, I couldn't argue with them too much. But still, the fact is there's a lot of code out there that has memory barriers, and it would be good if there was some way to have that as part of the standard. Anyway, before we get to that, what do you do instead of memory barriers? What they do is they have something called store, release, and load acquire. They have a few other operations, but these are the ones that I'm going to focus on. Yeah, that was my initial reaction. We have the guy from HP understanding that. And I wasn't the only one. Anyway, to be fair, they had a counter reaction as well when I was proposing my stuff, you know. I just, as it says there, I just barely resisted the temptation to point out that I think the first RCU patents are going to expire before good compilers come out with a new standard. What I did instead was I pointed out that there's a lot of other things that need the read side activity that RCU does. Okay, garbage collectors. Believe it or not, the C++ guys are working trying to get garbage collection to the standard. Okay, it's hard going, it's hard fought, but yeah, I don't know if they'll make this round, but they're working on it. There actually are implementations out there of standards.
That's from Hans Boone?
He has one of the early implementations. There's some other guys that are being, Howard Hinnant, I think, is working on some of it. He's the guy that's kind of in charge of libraries, and there's some other people that are really frustrated because they're doing this garbage collector work and nobody's trying it out, right? Sound familiar to any of you guys? But there's other things, hazard pointers, and type-safe memory, where once you allocate an object to a type, you leave it that type. You never free it. You kind of have a free list of that type. And if you do that, then these same sorts of things are needed to get high-speed read access. Anyway, it turns out that after a lot of screaming and shouting, they did convince me that store, release, and load and acquire actually work nicely on all parallel architectures, including Power, which some of the people that were goading me on were interested in for some reason. The trick is that on non-annotated machines, what you do is you prevent all the reorderings except for the ones involving store buffers. And the ones involving store buffers are the ones that are often most important. Okay? And what you have to do a load acquire store release, on x86, given the new Intel and AMD semantics, these came out last summer, and I think they're working on revisions to them to handle some of the SSE instructions, but with those new semantics, you don't need to do anything. Just the ordering saying that stores can't pass stores, loads can't pass loads, and if you have a load, a store can't pass in this direction. Just those three restrictions are enough to mean that you just generate code in order and the machine does the right thing on that machine. For Power and PowerPC, for the store you do as an LW sync, that's a lightweight memory barrier. And for load you have a conditional branch followed by an isync. Okay? You often need the conditional branch because you pick this thing up and need to figure out what the heck it is anyway. The isync means that any stuff coming afterwards is ordered after that. These are heavier weight than doing nothing, but on the other hand, Power gets the advantage of reordering instructions when it wants to, as long as you tell it not to. Itanium, well, as you'd expect, load, acquire, and store, release, right? And on S390 is also one where nothing needs to happen. S390 has even tighter memory ordering semantics than does x86. The other thing that, I guess I say up here that it's easy to explain. I suppose easier might be a better way to put it. But there's a nice analogy for store, release, and load and acquire. This in terms of sort of like publish and subscribe. And it's similar in some ways to RCU assign pointer for store release and RCU dereference for load acquire, which may kind of make people doubt my easier thing, but there you have it. It is used fairly heavily. The thing is that if you do a store release, the earlier store releasing has the effect of publishing the prior stores. When you do a load acquire of that same variable, the loads following that are guaranteed to see the stores that preceded the corresponding store release. And we'll see pictures of this later. So we're going to go through a few slides on this. I took a look through some of the SNPMBs in Linux, and based on a very small and probably not statistically significant sample, about half of them would just convert over trivially. You know, it's obvious that you just turn the one in WMB into a store release, the other one into a load acquire, and that's what they meant. And I think it probably makes it easier to understand, rather than just having a WMB with a comment on it that who knows which variable it really means in this sequence of code. Yes?
Why would you need to be set up to 0 on 390 there?
Okay, so this is not sequential consistency, right? Oh, I'm sorry. Arnd is asking why we need BCR 0,15 or 15,0. 15,0. It's the memory barrier instruction on the S390. And the reason is that remember that this particular thing did not disable ordering involving the store buffer. So in particular, if you have a bunch of store releases, the machine is allowed and the compiler are allowed to let those store releases happen in the order they want to relative to each other. It only enforces ordering between a store release and a corresponding load acquire. Whereas sequential consistency would require the machine to assign a specific order to all of those stores. Yes?
So the store release and load require take an argument? Or?
Yes.
Okay.
Yeah. Yeah, so let's go further ahead and see what they look like. So we can, and so you asked, here's what it looks like in C++. In C, there's a way of doing it where you have just a function call. So to do a store release, you do an f.store. So f is the variable name, and we have a method called store that stores. We're going to store a 1, and we're going to do memory order release. Okay, and that says essentially publish everything for this thing before you store the pointer. Now, this means that subsequent loads can be pulled forward, and on Itanium, and the compiler as well, can pull subsequent stores ahead. The only restriction is that prior stores happen before this store. Everything else is fair game. Similarly, on the load acquire, you have R1 equals, so putting the result in R1, you have your variable f, you have a member function load, and you say memory order acquire. Okay, and we'll see what other options you can put there on a later slide, but there are other ones. So what you do is you pick this thing up and you guarantee that any subsequent loads stay ordered after this load. In other words, any subsequent loads after this are guaranteed to see the stores that happen before this guy. So you publish here, you subscribe here. That means that any prior operations can be ordered after this. The only restriction is that we keep the stores above and the loads below. And you got it in tabular form there as well. And it turns out, again, that a lot of the weak memory barriers and also the strongly ordered systems just do this automatically. So it fits well not just with Itanium semantics, like hit me in the face when I first saw it, but also for most architectures. So this is kind of how the code might look, showing how things communicate. So and the thing is, unlike RCU, with RCU, this F would have to be a pointer to a structure that had A and B in it. All right? And again, you'd pick it up on the other side. Here, the difference between these and RCU is that there doesn't have to be a dependency relationship between the variables. You don't have to have a pointer to a structure that you're publishing. You can just have totally separate global variables like this. So a variable f, just some global variable, is going to publish A and B. You assign A to 1, B to 2, and then you say f.store, we're going to put a 1 in f, memory order release. And then what that does is it publishes A and B. Later on, somewhere else on some other thread, you do an f.load, memory order acquire. If that's true, if we saw the 1 that they stored, okay, initially 0 presumably, then we can pick up A and B. If we saw the 1, we're guaranteed to see those values A and B. Okay, the ones that were published by the corresponding store release. Now, this, of course, is a sort of a one-way thing. For example, if you somewhere else in your code assigned A or B, that might cause you problems. But again, remember, the C compiler is only required to maintain the semantics when you work on atomic variables like this one and this one. You have to have something else happening to prevent you from colliding with A and B, having two of these guys running in parallel. If you're doing concurrent stores to A and B, the compiler can do whatever it wants to, just like it can by the standard today. And I show how this might work, how you might do this in Power. You store to A and B, you have an LW sync, a lightweight sync, and then you assign F. On the other side, we if F, okay, and then we do an isync. This is a conditional branch. There's an isync after it, so that means that we have ordering of A and B after this, and the else clause, we can put that for completeness, and we're happy. You'd have similar, for something like x86, there'd be no memory barriers whatsoever. For something like Itanium, this would be a ST, REL. This would be an LD, ACQ. So a lot of people on the committee really, really did not like unadorned memory barriers. And the thing is, there's a large amount of existing usage. Yes?
Can you tell us exactly what you mean by memory barriers?
Okay, these would be things that, let me show you on the previous slide. So we want to know exactly what we mean by memory barriers. This thing right here is a memory barrier. It's not associated with a variable. All it does is enforce ordering the things before it and the things after it. Okay? So this would be an unadorned memory barrier, where the thing up here, the f.store, has a variable associated with it. So we went round and round on this. We started beating people over the heads with the existing practice, existing software, and eventually Bjarne had to intervene to keep them. What really was the motivation behind this, apparently, is that there's some distributed shared memory people who really, really hate the unadorned barriers. And apparently this particular subgroup in the distributed shared memory community wants to be able to kind of tag the stores with the variable that's associated with the memory barrier. And they hope to be able to kind of gather up the previous accesses and kind of send them out, communicate them, tagged with a variable, so that when you get the load acquire, you can go and kind of query something somewhere and get just those pieces in, instead of the standard practice of just having pages get shipped back and forth, kind of like cache lines. I don't know if that's a good thing or not, or if it works. They told me to go talk to the distributed shared memory people in IBM. I did, and they go, well, no, raw memories aren't a problem, and we argued back and forth, and it quickly degenerated into, he said, whatever. I just got to plug myself. Hopefully I won't have to FSCK next time I boot up. But what we eventually did after screaming at each other for a while is just decided to invent a mythical name. So if you have an unadorned memory variable and you care about having memory barriers associated with variables, there's a big long name in the standard that is a standard name that you associate with that barrier. Okay? It's kind of a made-up global variable. If you don't care about that, just emit a memory barrier. If you do care, well, here's your variable. And every release memory barrier without a variable gets associated with that global variable. And that seemed to make people at least, not happy, at least somewhat willing to go along with it. Yes?
What's the very long name?
What's the very long name? It wouldn't fit on the slide. Oh, I'd have to go back and look it up. I actually made it up, so I should know, but I guess the experience was painful enough I promptly forgot it. It's something, global variables memory or something, I don't know. Okay, so we had a big debate, and I've got a time check here. We've got 10 more minutes before. Thank you. So we had a big debate on what the C and C++ memory model should be. Theoretical people wanted sequential consistency. This on weakly ordered machines, this means you have memory barriers all over the place. So there's a lot of resistance to that. We beat them over the head asking for real-world use cases, which I have on the next slide. And eventually we came to the usual committee-style compromise, which is that sequential consistency is the default for unadorned stores and loads. In other words, if you have an atomic variable and you just load from it, it's going to be sequentially consistent. If you just store to it, it's going to be sequentially consistent. You have to use the explicit, f.store of whatever to get weaker memory access, which is okay. I think that's better documentation anyway. Now, it may be possible to relax that in practice, but the thing is that the theory of not quite as sequentially consistent but still useful things is very immature, and we weren't able to get things together in time to meet the standards deadlines. We did come up with some semi-formal semantics for these weaker things, and except for data-oriented dependency, which is still in progress. In fact, we were exchanging email about that this morning, and we had a little bit of fun getting that started, namely the bit about McKenney, what are you doing trying to drive RCU stuff and patents into the standard? There you have them. Every one of the real-world SC use cases that they were able to find for us. Every one of them. Only if there's a problem with the LCD projector or my presentation. Nonetheless, there's been a lot of people very comfortable with sequential consistency over the past almost 30 years. It's been known, and we just weren't able to prevent it, so there it is for the default accesses. So atomic operations, I'm not going to go into a huge amount of detail, but they have the atomic operations you expect. You can do compare and exchange, you can do atomic increment, fetch and add, things like that. Now, the thing is that C++ being what it is, this atomic is kind of a template thing. That means you can make a big, long, hairy data structure and do a compare and exchange on it. And the compiler is supposed to do whatever is required. I would strongly recommend that we make sure we keep that out of the Linux kernel. Other projects might want to do what you want. But fortunately, after what they did was they put in a compile time thing that you can query about a type and say, does this thing really, if I do this, atomics on this, are you really going to generate atomic instructions, or are you going to make a lock for me? Okay. And so you could do something like check at some point and see whether that data structure on a given architecture atomically manipulated as opposed to some invented lock somewhere doing it for you. Now, that at least allows you to see if the compiler is doing nasty things to you. I can't imagine, I have a hard time imagining a piece of software that would actually sample that flag at runtime and do something useful with it, although that may be a failure of imagination on my part. There have been a lot of things that I would have sworn impossible that happened, including some things I've done. This is kind of a list of the things we had there. Relaxed means you have the atomicity of picking it up, putting it down, but no ordering whatsoever. Depends is the thing I'm trying to get into, which is essentially what RCD turns into. Acquire and release we've talked about. We can do both acquire and release on the same operation as you might for an atomic operation that gets from one place and puts to another. And sequential consistency is the guy, if you're a theoretician, this is what you know and love. The other thing that they did that's really cool, in the C standard, there's only one type of variable that you can safely use in a signal handler, and that's sigatomic T. It's like 1 byte, and you can store to it, and that's it. One of the things they're doing is they're making it so that variables can safely be used as signal handlers. But for the primitive types, the ones that say, yes, I don't need a lock. The compiler don't have to generate a lock for me.
So how would the atomic types be in C?
How would they? Oh, okay. How would the atomic types be in C? If I remember correctly, you'd have atomic underbar int for an atomic int. And I think that C is only doing the basic types. All right. Of course, I think it allows atomic underbar double. So just because of the basic type, as Grant pointed earlier, doesn't necessarily mean that you get atomic operations on it, really. Okay. So these are some other concurrency things being considered. I'm not going to belabor those. What's this mean for free and open source software? It turns out that multi-threaded software actually favors free and open source. The thing is that multi-threaded software requires global design constraints. You have to avoid deadlock. You can have a deadlock cycle going through any arbitrarily long part of your code. Any part of your code might be involved. It's a global property. You can have 5 pieces of code you put together. Any 4 of them won't deadlock. The 5th one adds deadlock, whichever one it is. It can happen. Data structure partitioning also has to be done globally. And lock and memory contention are global properties. The bit about showing you the code means that any developer anywhere can verify that these global properties actually hold, or find places where they don't, more likely. Software always has bugs, right? It also works in tightly controlled proprietary environments. Like back at Sequent, there was a bunch of us. We all had access to the code. We were all in one place. We didn't have the benefit of outside review, but at least all of us could see the code and all of us could verify these properties. It doesn't work so well if you have multiple proprietary things working together where nobody can see a view of the code, so that's one of the reasons why Linux binary modules and drivers can be painful at times. There is some potential, if they get this right, that we might be able to move some of the low-level concurrency code in a system.h and atomic.h in the Linux kernel into the compiler. And if we did that, the compiler might be able to do a better job of generating the code than we can, because it'd be able to look at different combinations of them and say, oh, well, you've got 5 memory barriers here. We can just get rid of them because only one of them is really needed. Of course, this would require some changes because the standard is a little bit different than what the Linux kernel is doing. There is no RMB, for example. All right. On the other hand, there's no machine I know of that actually does an RMB natively, so that may be just as well. So some lessons learned. Get involved early. This would have been a little bit less painful had I gotten started in 2005 instead of late 2006. On the other hand, at early 2005, we didn't have some of the better explanations for RCU, so it might have been balanced by the difficulty of explaining RCU to the committee. I don't know. But starting in 2005 would have had a better chance of providing a good alternative to SC. If I started in 2005, we might have had the time needed to really get that nailed down. Although how I would have had time to do that while doing real-time RCU, I don't know. But yeah, there you are. Fortunately for me, there are a lot of Linux community members that have been involved in the C++ standard for quite some time. So when I first presented dependency ordering, it would be an understatement to say that the committee was not amused. In fact, they encouraged me in subtle and not so subtle ways that I should drop this proposal and get on with life. As some of you may be aware, I can be a little bit stubborn if the need requires. So, and I wasn't going to go back and say, they didn't like it. So the rules say that you can present it to the full evolution committee, and I invoked my right under those rules. So here I am in front of the evolution committee. Bjorn sitting over here. I'm presenting the slide set about dependency ordering in RCU and how it's useful and why they need it in the standard. And I'm seeing people. The way voting works in that sort of a venue, where you're just voting on whether something is likely to go forward or not, is a straw poll. Everybody present can vote, and all the votes count equally. You can vote strongly in favor. You can vote weakly in favor. You can vote neutral, weakly against, or strongly against. I knew there was going to be one vote strongly in favor. And judging by the way they were reacting to the presentation, I expected exactly one vote. To my surprise, there was like 6. And in fact, the vote came out kind of even. There was about an equal number of people voting for all the 5 of the possibilities. I was kind of like, oh, well, you know, it's better than I thought it was. Bjorn whispers to me, those are Linux guys voting for you. So there have been people involved. It's one of these things that we've been saying for a long time. There are more ways to help open source than just contributing code, reviewing code, finding bugs, documentation, participating in standards. So we need to make sure we're reaching out to members of our community that are doing that. Academia is important. It's important even if you don't think even if you think they're talking rot, as I did, because people listen to them. The other thing is that when standards people say it's undefinable, it's often the case they really mean I don't understand it. So there's a lot of different standards. I've been involved in C and C++. That's one of them. It's the one I happen to know. I'm going to talk about how you get involved in that if you want to, but good Lord, how many standards are there out there? A lot of them are valuable. So this is the way the Standards Committee worked the last meeting. ISO WG21 is an international body. Every country gets a vote. Every country that shows up gets a vote. The last meeting, those are the countries that showed up. Now, with France, if you're French, you get involved. There's this AFNOR. I don't know what it stands for. That's a standards body within France, and you can influence them by whatever rules they have. DIN is the one in Germany. I don't know what the heck the situation with Switzerland is. As near as I can tell, the guy from Switzerland is just a hobbyist to convince the government that he should represent them. I don't know. So, you know, some of you guys that aren't from one of these countries might have that option. You know, find or form. Every vote from every country is equivalent. Except for the U.S.'s. The U.S.'s I'll get to actually counts less than other people's. I wonder, these guys aren't from the U.S., are you? UK, there's something called BSI, standard body. U.S., there's ANSI XJ16. The reason U.S. vote counts less is that ANSI XJ16 is an open standards body. That means anyone in this room, or anywhere, could pay your $80, attend enough meetings. If you want to stay a voting member, you have to attend a certain number of meetings and you have to do a certain amount of work. You can vote. Your vote counts just as much as any other person on the committee, regardless of your nationality. The vote of ANSI XJ16, all its members, American or not, determines the U.S. vote. It's just direct. They count. What will happen when they vote is they ask for ANSI XJ16 to vote. The people with that raise their hands if they are voting members, and then they do simple majority or whatever, depending on the type of vote and what the rules are. But they use that to directly mechanically determine the U.S. vote. On the other hand, there's a lot of people on XJ16. If you go with your own country, you actually get a vote yourself. Anyway, so IBM Legal sponsored this, and actually in the past 5 years I've gained a much greater appreciation for their services. Yes, Grant.
Yeah, so I just have a comment and a reference.
Okay.
And the comment was something that I discovered when working on performance monitoring.
Can we give him a mic? I'm not going to, no way I'm going to repeat this.
Okay. So the reference is the i64 Linux book, has a great explanation of memory ordering and how it works, and the canonical usage in the Linux kernel.
Okay. Sounds like it. Okay, well, I can either hand you the mic or you can hand me your laptop. Pass that up, please. Yeah, it is.
Yes, it is. Okay. So let me get this up here again, because I have to read this. The statement that I ended up writing, this is after consulting with Intel architects, and this is playing, post office, where I would ask the question to our architects, and they would go and talk to their architects, who would talk to their hardware implementers, and it sort of came back this way. The thing was that memory ordering imposes no constraint on non-load store instructions. And you think, okay, this talk was about data, but I was trying to measure the performance of data accesses, and that talks to CPU registers, which are non-load store instructions. Okay, so there are probably other cases where that comes up, and people should just be aware of that. So this whole ordering limit is sort of constrained in terms of what it applies to.
Good point. I wasn't worried about register ordering, and I should be worried about my cable here. Okay, 5 minutes for questions. More questions? Rusty.
So the kernel has a current global. It's actually a macro that gets the current variable. Now it turns out that because of the way we use memory barriers around locking, we stick that in a local variable, so it's not forced to be reloaded on every occurrence. Because every time there's a barrier, that gets thrown away, even though there's only actually one function that can change it, and that's schedule. If you don't call schedule, it will not change. And it would be nice to have a way of defining that in the language. That you could say, this doesn't change, all independent of store barriers, memory barriers, everything else.
And the way you would,
except for here.
okay. So what the point is that there's a variable called current that points to the current task, and it doesn't change very often. Now what you would do, I think, in this thing is you would define it to be an atomic pointer. And well, okay. Let's not worry about exactly where it changes. It changes somewhere, but not very often. And so what happens is that you would make it be an atomic, and you would normally do a load memory order relaxed from it. What that would do is it would say load this thing only once, but it would not do any memory barriers. And the other thing is if your other barriers were associated with variables rather than raw ones, the compiler would be able to wander things across them.
But would it be invalidated by calls?
It might well be unless you had a lot of interprocedural analysis, which we don't yet.
Right. So that's the whole key. Once you have a call, that's like the memory barrier.
So how long do you think it'll be till we have GCC? The point was that if you have a call, a function call, then the compiler normally just dumps everything on the floor at that point, all its temporaries.
The reason this up is because I've hit the opposite problem. GCC did not invalidate the global register across the call.
And sometimes there's good reason for it doing so, and sometimes it fails to, yes.
Right. Anyway, so that was a mysterious crash I had to track down for 2 weeks.
And finding it can be really difficult. Yeah, so I suppose one could imagine GCC eventually doing really vicious interprocedural analysis, but even then you have things like pointer aliasing problems where it has these two pointers that it has no idea or can't ever point to the same thing.
And often in the implementations of the context switch, it's down, all the way down at the bottom, it's some assembler stuff, right?
Yep.
Which is where the current register is actually modified, because by implication, you're trying to be safe and you're keeping it all from the compiler anyways.
So the lesson is hide it from the compiler, unless you.
Exactly.
So what you're saying is interprocedural analysis would be a bad thing if we ever do it.
As long as it told you the same thing at the bottom, said, oh, you invalidate everything.
Okay, yeah. So even with this stuff, we'll need